So here, let's define our function. So let's call it function 2. Now this is going to be a function. Now what is the variable we want to solve for? Let's put that first. This is the surface temperature. Yes, there's a lot of unknown variables in this. For some of them, there's only one unknown, but we have a lot of variables. So you can put them all in so that you can change. But you want the one you're finding the root with respect to as first variable. Okay, so all the other arguments are what? We have the temperature infinitely far away. We have the temperature on the inside. We have the area. We have the resistance, total resistance. We have the convection heat transfer coefficient. We have epsilon. We have the emissivity. And then we have sigma. Now, sigma is the Stefan-Boltzmann constant. So when you're defining a function, you can say things by default will be defined. So this one you never want to change because it's a fixed constant. So in SI units, that's 5.67 by 8. So if you say that it's equal there, we don't need to input this. It'll just default this unless we define sigma. And so this is in SI units. And what we will return is the function I showed you on the notes. So for example, this is T infinity minus Ti divided by A times R total. And this is going to be minus H plus epsilon times sigma times Ts plus T infinity, okay, times Ts squared plus T infinity squared. And this is going to be times the whole second part of this after the minus sign, T infinity minus Ts. Okay, so this is the function I showed. Complex nonlinear function, how we're going to solve this. So again, we can visualize this first. Okay, so let's visualize it. So let's make a list of temperatures. And
okay, visualize it. Visualize first. So just now the graph here also is visualized, then you can estimate where is the root then.
NP dot Lin space. So we know the inside wall temperature is going to be 308. Outside is going to be 283. So let's make some linear space between, let's say, 283.15 to 308.15. These are two extremes. We know that the temperature of the surface is going to be somewhere in between those two. We'll say, 1,000 points in between there. So we need these values to be able to evaluate the function. And now let's plot it. Okay, so I'll do the same thing we did here. We can just copy this, and we'll make this plot 2. We're going to plot this for temperature list, and this is going to be function 2, and evaluated the temperature list values. And this is going to be the 0. This is the root, so we're going to find where it equals 0. And plot here, and plot pops up. Oh, excuse me. Okay, so now what we'll need to do in this function is it's not just, okay, the first one we did had one variable. Now when we have these more complex functions, we have a lot of variables, okay? So we're going to put this list of temperatures for the surface temperature. This is the one we don't know. We're going to solve for the root function of this. All the other ones we know, okay? So these are inputs. So the next one we need is T infinity. So this is going to be 283.15. T in the inside is going to be the next one, is going to be 308.15. Then you have the area is 1.8 meters squared. Our total is 0.25 Kelvin per watt. What else do we have? The H is next. That's a 2 watts per meter squared Kelvin, and the emissivity 0.95. And then I don't need to input sigma, a variable for this, because it'll default this value, which is fixed universal constant. Okay. Now we can plot this, and this is what you do. There's going to be a root somewhere around 290 Kelvin. Okay. So now we can use this for the root finding. Okay. So let's do it. Let's say the surface temperature is going to equal fsolve is this root finding function. Now we need to input the function. So this function 2. Now this is where it gets a little different when you have a lot of variables in a function. because here we had one variable. So you put function 1 and it knows that, x is the variable. Now function 2, there are actually a lot of variables. So what it's going to do is it's going to take the first input as the variable that matters. For the root finding. So we need to give it all these other arguments though, so it knows what to put in. And so let's put function 2 in, and it'll use TS as the one to solve the root with respect to. And then you give it our initial guess. The initial guess we can see from the plot is around 290 for the root. And then what you can do is you can say args. Okay, so you can see this in the definition. See in this function description, it tells you that you can put in arguments. Now, what arguments means is everything that comes after the first variable. Okay, these are going to be the arguments that you can input into SciPy. So here we need to put t infinity, ti, a, r, h, epsilon. So okay, let's do it. It's going to be all of these variables will be the arguments. So I hope you understand how to input your different variables. Variable you want to solve the root for as a function of, and then these are the arguments. And anything that you put an equal sign next to will be fixed. You don't need to input those to default as value. And by the way, you can get rid of all of these and just define them in the function. But for example, if you want to change the convection coefficient, it's really easy to just change h as opposed to having h defined already. This is just better practice to leave undefined, input them as arguments. But there's so many different ways to do this. It doesn't matter. Okay, so this is going to be fsolve. All we've done is add this extra one here. And we'll say, just to be clear, this is in Kelvin, SI unit, okay? So we evaluate it, let's look at it. TS, about 290.977 Kelvin. And if you want to put this, something reasonable, TS in Celsius, it's going to be TS minus 273.15. Check this, TS in Celsius is about 17 degrees, okay? So if you, what do we say? The one surface at 35, the other is at 10. So in the
Okay, so I'm a bit curious also. So I just now I show you about this. Okay, so you can find that this is going to, we have 5 minutes more. Okay, when you try to plot this, okay, so when you try to plot this, your W is variable. When you try to plot this versus omega, let me try to do something. Okay. When you try to plot, so for example, if this is omega, and then if you try to plot the lambda, this, okay, when you try to plot this, maybe you see curve. So I use